Hi, my name's Lucian Wishick. I'm telling you 3 essential tips for using async correctly in your code. This is tip number 2. It's about I/O and CPU-bound work and how important it is to distinguish between the two. Let's hear what a user had to say. This user, he said, "I'm now looking at the biggest user complaint about a slow-running operation in my ASP.NET Web Forms page. Essentially, the page loads some data, and I'm wondering if it would be the best approach to use the task parallel library." He was writing some kind of Zillow housing app. He said, "Essentially, the page loads some data, and I'm wondering if it would be best approach to use the task parallel library. The method itself deserializes an object, and depending on user choices, it can call the method in a for each 26 or more times, the result of which I bind to a grid panel." He said, "The deserialization itself is where 99% of the time is being spent." Well, that's a brilliant start. He used profiling. He identified what was the problem area. The punchline, though, is that he hadn't clearly understood the difference between CPU-bound work and I/O-bound work. And depending on which of the two it is, that will change how you should parallelize it. We'll get to that in a moment, but let's look at what the customer started with, and we'll take him at his word that the deserialization work was doing a lot of compute-bound work, and we'll see what happened. This was the code he wrote, this Zillow application. He called load houses sequentially. It went one by one. It called this deserialize method, added them to a list, and then it data-bound them. How did the code actually work? Let's just draw the control flow. A request came in. It did work 1 for the first house, work 2, 3, 4, 5, all in order. And if each house takes 100 milliseconds to deserialize, then it will take 500 milliseconds to deserialize them all. That's fairly straightforward. So what the customer did, let's look at this code. He decided he's going to try and use task parallel library. He was going to use parallel.for to make it work better. So he called load houses in parallel. He did parallel.for, and he had a lambda in here. And this lambda is the work that's going to be done for each house. It's going to deserialize it, add it to the list, and then return the list. Let's see the flow diagram for how parallel.for actually works. Well, the request comes in. It comes into parallel.for. And a neat mental model for how parallel.for works is that there are going to be 5 work items. I put them inside this drum that are going to have to be done at some stage in the future. So it's parallel.for, which means the 5 lambdas are going to be executed eventually. So parallel.for is going to make the thread pool do the 5 pieces of work. And the thing about the thread pool is that it will run them on as many threads as will be fastest. My laptop that I'm doing this demo on has 2 CPU cores, a boy core and a girl core, you can see from the colors. So using 2 cores will be quickest. If each request takes 100 milliseconds, then you can see we're getting the answer out in 300 milliseconds. That's an improvement, down from 500. Actually, it might not be an improvement, you know, because if we're running this ASP stuff on a server that's having to handle other requests as well, then probably the other core is busy, so we'll only be using 1 core here, so parallel.for won't actually buy us anything. Parallel.for does not buy us scalability on a machine that's already working flat out. Actually, hold on just one moment. What the heck kind of deserialization takes 100 milliseconds? That's a long time. You know what I think? I checked with the customer. 100 milliseconds is an eternity. The customer said, it's not doing deserialization like I'd think of doing it. Actually, what he called deserialization was going to a whole bunch of databases to get back more information on each house. That explains why it was taking 100 milliseconds. And that totally changes how we should approach this problem. And whenever you're writing async code, I want you to think very carefully, am I writing CPU-bound work, or is it bound by the time of network requests? Well, let's look back here and see what the code was actually doing. He started off by writing sequential code. He did it one after the other, and you can see that we started the first house in his original sequential code. His code just sat idle there for the first 99 milliseconds until it gets back the response. Then it kicks off the second request, sits idle for most of the time, gets back. And that's why it was taking 500 milliseconds. But then when he did parallel.4, actually what happened is subtly different from what we saw before. Well, as we said, it started off knowing that it has to do 5 work items in the thread pool. And we'll say again, the thread pool started at 2 threads because it knows my machine has 2 cores, so 2 threads is a good initial guess. But after a time, the thread pool is going to realize, hey, my 2 cores are pretty much idle. They're just sitting there twiddling their thumbs. I'm going to try injecting another thread to see if that speeds things up. Maybe even it'll inject another thread. So we might end up having 4 of them and then doing another one. Maybe it gets in time. The question is, how quickly does the thread pool respond? Pretty slowly, you know, maybe injecting a new thread. It's got a hill climbing algorithm. I'd expect it to respond by injecting about 1 thread per second. So this parallel.4 is not a way to get responsive code. If we suddenly get a big load of requests, the thread pool is not going to scale up quickly to respond to them. Let's get away from this and let's draw a diagram of how ideally the code should work. Ideally, the request comes in and we just want to kick off 5 requests to the database quickly, one after the other. Bang, 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 bang. It takes very little time to kick off a request, like microseconds. Then, later on, 100 milliseconds later, all of the requests will come back. They'll come trickling in. Maybe they'll come out in the wrong order, maybe whatever. It doesn't really matter, but they'll all come back and we can gather all of the results and we'll have the response coming out in just 100 milliseconds. So this is by far the ideal way to architect this program. We're going to look at the code for how to achieve that. But first, let's review what we've said. We've said that it's crucially important to understand, are we writing CPU or I/O-bound work? CPU-bound, it means things like link over objects or big iterations or compute-bound inner loops. Now, parallel.forEach and task.run are a good way to put CPU-bound work onto the thread pool. The thread pool will gradually feel out how many threads are needed to make best progress. However, using the thread pool, using background threads, will never increase the throughput on the scalability of a machine that's already under load. So the guidance is, for I/O-bound, I put it in quotes, for I/O-bound work, it's not really work, it's just twiddling your thumbs waiting for a response to come in off the network. For I/O-bound stuff, use await rather than background threads. But for CPU-bound work, that's when you consider using parallel.for or task.run. Let's look at how the ideal code would work. Here, we've called it load houses async. It's an async method that returns a task of a list of houses. What do we do? Well, what we said is that we're going to kick off 5 requests. Bam, 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 one after the other. So we're calling house.loadFromDatabase async. That just gives us back a task, and we'll add it to a list of houses. Later on, we can await task.whenAll, so we can await until all of them have finished, and then we can return it. Well, that was really great. That was a very easy way to take code that was not really CPU-bound, that was really I/O-bound, and parallelize it for maximum scalability and for best time to first byte. I've shown you that side for I/O-bound code. I also want to show you the best practice for CPU-bound code. To come clean, in these 3 essential tips for async, in all of them, I wanted to pick example code that real-world users had run into real-world situations. But when it came to finding CPU-bound code, I was kind of at a loss. The reason for that is that CPU-bound code is quite rare. Very few people will be writing it. So I had to invent this one myself. What I wrote, let's look at the code. It's a desktop application for doing financial analysis. Actually, it's doing option pricing. What a financial firm does is they simulate 1 billion different ways that the stock market might move over the coming year, each of them equally likely, and they figure out whether the option will be a good deal or a bad deal over all of those 1 million possibilities and how much it will pay out on each. That's this function of this quant.simulate stock price method. It's very clearly CPU bound. Actually, I didn't do it. I farmed it off to the rocket scientist guys in the back end, the financial analysts. They actually wrote this code in F#. I think what you'll see quite a lot is for the heavy-duty numerics, the analytics being done in F# because it's a perfect language for it, and because the quants, the analysts, they understand it. But then we'll write the UI on top of it in VB or C#. Anyway, back to the code. It's very clearly CPU bound. You've got this for I equals 0 to 1 million. Do a CPU bound piece of work. So clearly this background work, this CPU bound work has to go on the thread pool to improve responsiveness. We've got 2 ways to put it onto the thread pool. One is parallel.for and one is task.run. I could have used either, but I'm going to use task.run here just to show you. Sometimes people ask, why didn't you just put it inside an async task returning method? That misses the point. Putting the async modifier on a method does not put it onto the thread pool. It never, no keyword in the language will put work onto the thread pool. The only way that work is going onto the thread pool is if you call an API that does it, like task.run or parallel.forEach. Well, what are we going to do? Here I chose to use task.run to put it onto the thread pool, and the best practice is to keep the scope of that task.run as small as possible. Limit it only to the computational inner loop. That will simplify our code. Here I've made it pretty much as small as I could. I made it small so this code doesn't try to update the UI. All it does is it has a return statement. So the UI can do var expected payout equals await task.run, and there it can get the answer back inside expected payout, and it can assign it into the UI itself. What's really great about this is that you probably remember using background thread in the past, figuring out how it updates the UI. What we're doing is we're looking for ways where the background thread never needs to update the UI itself directly. We're trying to get a good separation of concerns. Actually, in the UI in this program, because it was taking about 5 seconds, I really wanted to have a progress. I wanted to have a progress bar just to show how it worked. Once again, normally if we're running in a background thread on the thread pool, we can't update the UI from the background thread. In particular, inside the body of task.run, it can't update the UI directly. So, what's the standard pattern now new in .NET 4.5? It's to use this iProgress of T type. Here I've written iProgress of int. I created it with a progress object, which takes a callback. And what it's doing is it's assigning the value I into a progress bar, a UI element. So whenever the background thread wants to report some work, it calls progress.report. That's all it does. It has a good separation of concerns. It doesn't care how the iProgress type is implemented. All it does is report progress, and then progress through this thing, through this progress type, gets marshaled back to the UI, so the UI thread can update itself. There we've seen how to use task.run to put a computational inner loop onto the thread pool. There are some more things to talk about around here. WPF specific, how data-bound properties work. New in WPF 4.5, how collections can be updated from a background thread. Key patterns to recognise when code looks async but isn't really. I've put all of these again on the slides that you can download from Channel 9 or from my blog. But I don't want to go into those. I want to really reinforce to you this key, essential tip number 2 for how to write async code correctly. The important thing is figure out if you're writing IO-bound or CPU-bound work. For IO-bound work, it's not really work, use await. Don't use background threads, just await. You can await task.whenAll, task.whenAny. If you do have CPU-bound work, things like link over objects, big iterations, computational inner loops, that is when you're going to use parallel.forEach or task.run. Thank you.